Welcome to Online Algebra 2. This is section 5-3, solving polynomial equations. So our objective for this section is to solve polynomial equations by graphing and then to solve polynomials by factoring. Factoring, we're going to use all sorts of different factoring techniques. And for graphing, we'll pull up some graphs on a graphing calculator, specifically Desmos. What you should know is that if x minus a is a factor of a polynomial, then the polynomial has a value of 0 when x is equal to a. It's an intercept. If a is a real number, then the graph of the polynomial has a comma 0 as its x-intercept. It's also a root, and it's also a solution to the equation. So, how do we go about solving polynomial equations by factoring? First, we're going to set it equal to 0. So write the equation in the form p of x equals to 0 for some polynomial function p. Then we're going to use some sort of factoring technique to factor the polynomial. We're going to focus on a few specific ones in this section. And then in the next sections, we're going to look at a more general way that we can solve things that don't necessarily factor. Once we have the polynomial factored, we're going to use the zero product property to find all of the roots. Okay, so let's start with this one. The first step with the polynomial equation is to set it equal to 0. So we change this to 2x to the third minus 5x squared minus 3x is equal to 0. Okay, so now I notice that it doesn't have any common factors except for x, so I can take that out. So 2x squared minus 5x minus 3. Now I can factor this with polynomial techniques. This is the factors of 1 and 2 times the factors of 1 and 3. Those are both prime. So I know that this has to be x and 2x. And then there has to be a 1 and a 3 in one of these two spots. So in order to get the inside and the outside pairs to combine to -5, I'm going to put the -3 there. That gives me an inside pair of -6. The plus 1 right there, outside pair of 1x, gives me -5x. That is the guess and check method of factoring a quadratic. Okay. You could also use the AC method if you wanted to write it out and then factor with grouping. So from here, we now have 3 different things equal to 0. 3 linear factors multiplied together equal to 0. So the solutions using the zero product property are 0, 3, and x. X is equal to -1/2. Okay, so I took all my 3 factors, I said each piece equal to 0, and I have my 3 solutions. Okay, sometimes it's that easy, sometimes it's not. So for this one, again, set it equal to 0. So we have 3x to the 4th minus 6x to the 3rd in standard form plus 12x squared is equal to 0. Now I can factor out a, well, first of all, before I even do anything, I factor out variables because I don't want to lose any solutions. But if I have a coefficient that's common, I might as well just divide it out. So I can divide this entire side by 3 as well as that side. So that now changes it to x to the 4th minus 2x to the 3rd plus 4x squared. Now I can factor out an x squared. Give me x squared minus 2x plus 4. Well, here's a problem. Because factoring this, I'm trying to find the factors of 4 that add to 2. Well, the factors of 4 are 1 and 4. They add to 5. 2 and 2, which add to 4. So there are no factors of 4 that add to 2. So if I want to find the solutions to this piece of my polynomial, I must use the quadratic formula because it is a quadratic. Okay, it's x squared. It's a quadratic. So we're going to use the quadratic formula where a is 1, b is -2, and c is 4. So that means x is going to be equal to -2, so +2, plus or minus square root of -2 squared is 4, minus 4 times 1, which is 16, over 2 times a, which is 2. So we have 2 plus or minus the square root of -12 over 2. The square root of -12, when negative comes outside of, I'm going to need a little more room. The negative comes outside of the radical and turns into an I. And then I could simplify the rest of the radical to 2 plus or minus square root of 12 simplifies to 2 square root 3. So it's 2i square root 3 over 2. And all the 2's cancel out to give me 1 plus plus or minus I radical 3. So this is a polynomial. This is a 4th degree polynomial. So my answers are this one. Don't forget that one. That was right in front. 0 with a multiplicity. The multiplicity of 2, because it happens twice, because it is squared, comma, 1 plus or minus I square root 3. And those are 4 answers. 2 answers, 3 answer, plus 4 answer is the negative. So for each of these, I still used my basic techniques, right? My basic quadratic techniques, my basic factoring techniques in order to get all the answers. Let's try a couple more with the guided problems. Luckily, the first guided problem is already factored for me. Well, that's nice. So I can set each factor. Equal to 0. So I can say x squared minus 1 is equal to 0. So x squared is equal to 1, square root both sides, and we get x is equal to plus or minus 1. But this side, right, gives me, when I square root both sides, x equals plus or minus 2i. Okay, so those are my 4 answers for these two. For this one, let's see what we got. X to the 5th minus 5x to the 4th. Add 2x to the 3rd to both sides. And you get 6x to the 3rd. And now it's equal to 0. Factor out an x to the 3rd. And we're left with x squared minus 5x plus 6. Very similar to the first problem in that we have able to factor this and factors of 3, x minus 3 and x minus 2. So now my 5 answers are 0 from this one with a multiplicity of 3, positive 3, and positive 2. Okay, so for all those problems, we didn't really do any new technique. We didn't really do something that was different. The basic techniques for factoring is take out a GCF, which we did that, right? You take out an x squared, you take out a polynomial. Factor a quadratic trinomial, either with the guess and check method, the AC grouping method. Recognize that it's a perfect square. Recognize that it's the difference of 2 perfect squares. Really won't have to worry about this too much where we have radicals in the factoring. We're going to stick with straight perfect squares for that. And factor by grouping, which you should be pretty comfortable with all of these techniques from chapter 4. Okay. Now, we're going to add one more, okay? And it's called the sum or difference of two perfect cubes. So you recognize this by having two perfect cubes. That's not this. This is a binomial cube. That's not what we're doing, okay? What I'm talking about is something like this plus 27, which is 3 times 3 times 3, a perfect cube. So as long as both of these are a perfect cube, and they're the sum or difference for perfect squares, right? We're only looking for the difference of perfect squares. The sum of perfect squares factored with imaginary numbers, but the sum or the difference of perfect cubes both factor. And we're going to remember this technique, this pattern of the signs, by remembering an acronym. SOAP, okay? So think you want a factor, you want two perfect cubes, you go to your nice bathroom and you use a cube of soap to help you factor. Not really practical, but it's just a mnemonic device. And this stands for same sign, opposite sign, always positive. Okay? And what that means is that if you're factoring the sum, this is a sum, difference, always positive. Now the rest of this, you're going to have to sort of remember that. And it looks kind of like a perfect square trinomial, but notice that a perfect square trinomial has a 2 there, okay? Which means that this thing right there is not going to factor, okay? And without remembering, and the difference is the same way. So difference, so same sign, opposite sign, always positive. Now, the reason why it's good to try to remember this formula, or both of these formulas, is that if you wanted to try to do this the long way, if you wanted to try to factor a generic a to the third, b to the third, and see why it actually works out to this, it's actually kind of complicated. So if we have a to the third plus b to the third, there's really nothing in common there. There's nothing that we can take out. So we're going to change this a little bit. I'm going to put some space in here. And then we're going to add some stuff to this. And we're going to add an a squared b. But if you add an a squared b, you have to take it away, or else you've changed the equation. Okay, so then I'm also going to add a minus ab squared. And if I put in a minus ab squared, I have to put in a plus ab squared as well. Okay, now I still have my same equation, a to the third plus b to the third. The rest of the stuff all cancels out. But what you should notice is that you can now factor this with grouping. These two both have a common factor of a squared. What's left over? 1a there, 1b there. Okay. These two both have a common factor of negative ab. What's left over here? Well, I took the negative out. I took 1a. I took 1b. There's an a left. Put the negative out of here. Took the a out. And there's only a positive b left over. Okay? And these two have a common factor of b squared. And there's an a plus b left. Factoring by grouping, we now get a plus b times a squared minus ab plus b squared. The formula for the sum of two perfect cubes. Notice, same sign, opposite sign, always positive. Okay? And again, if I had reversed these two, if I had put the positive and the negative, it wouldn't have quite factored so nicely. All right, so the shorter answer is that you don't want to have to do this every time you want to try to factor this. So the ideal thing is to remember that formula and use the acronym SOAP to help you. All right, let's try some more factoring. So the first factoring is not that technique, right? It's not the SOAP technique because it's x to the fourth. But watch what happens. When we set it equal to 0, we have this pattern, and it looks like a quadratic. Okay, so right now we don't have a good technique that we can use if it's x to the fourth, unless you have something like this. Remember that a quadratic went ax squared plus bx plus c, right? The variable went down 1 each time, 2, 1, 0. Here, the variable is going down by a degree 2 each time. And in fact, we can factor this just like a quadratic, but instead of putting an x there, because that would make my first term x squared, right, x times x, if I put an x squared, now x squared times x squared is x to the fourth. And if I put a minus 4 there, a plus 1 there, you'd see that the middle terms now have an x squared. Okay? So as long as the variable term goes down by some number and then to 0, you can use a quadratic-like technique. Of course, we're not done with this yet. Now it's a product. Set each one equal to 0. So x squared is equal to 4. Square root that, you get plus or minus 2. Here, set it equal to 0. Square root a negative 1, and you get plus or minus I. Okay, so it doesn't have to be a quadratic to use a quadratic technique. Let's try my new cubic technique. Okay. Now, the way you recognize to use the sum or difference of cubes is it's only going to be 2 terms, and they're both going to be a perfect cube. Well, what numbers are perfect cubes? Right, 1's a perfect cube because 1 times 1 is 1. 8 is a perfect cube. That's 2 to the third. 27. 64. 125 is 5 to the third. 6 to the third is 216. And you get the idea. Just like, and you can calculate the rest of these going up to 10, going up to 1,000. But just like you would recognize a perfect square, like I see this, oh, I recognize that. It's 7 squared. You should also kind of get in the habit of saying, that number looks familiar as well, 343. It's 7 to the third power. Okay, you don't necessarily have to memorize all these because you can get them on a calculator pretty easily, but it's good to actually be familiar with them. Okay, so let's go back to this problem right here. You have 2 perfect cubes. It's a difference. So that means I'm going to factor this to x, same sign, opposite sign, always positive, 1 squared. Okay, this is a, right, here's the formula, right? A minus b, or let's go a to the third minus b to the third is a minus b, a squared minus plus same sign, opposite sign, always positive. Okay, so in this case with a 1, nothing really happens. The middle one is the one that everybody always mistakes, right? It's just this times this, but don't take the sign with you. Let the SOAP acronym help you put the signs in the right place. Same sign, opposite sign, always positive. Okay, now, this will have 3 answers. Here's the first. This one will never factor. You will always have to use the quadratic formula, and you're always going to get some sort of imaginary number having to do with a radical 3. Okay? So, let's get it. So x is going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, which gives me negative 1 plus or minus the square root of negative 3 over 2. Nothing to do there except for to take the negative out and make it an I, which gives me negative 1 plus or minus I radical 3 over 2. And you can split that into two fractions if you wanted to. Negative 1/2 plus or minus I radical 3 over 2. There's my two answers. There's my third answer. Okay. Always, when you factor the sum or difference of perfect cubes, you will get, always, you will get one real answer and two imaginary answers. Because it's a transformation of the cubic parent function, shifted in this case down 1. If you remember what the cubic parent function looks like, kind of something like that, it never loops back down. It will only ever cross the x-axis one time, which means it will have one real zero and two imaginary zeros. Let's try some of these. Okay, so for A, that is two terms. X to the fourth doesn't matter. It is the difference of two perfect squares. So that factors in the x squared minus 4, x squared plus 4. This is again the difference of two perfect squares. X plus 4, x minus 4, 2, sorry. X plus 2, x minus 2, and x squared plus 4. Set those all equal to 0. And so we get x is equal to, you didn't even have to do this. You could have just set them equal to 0 right there. That's going to be plus or minus 2. And for this one, it's going to be plus or minus 2i. Okay, for the middle term, or for the middle one right here, we get x to the third plus 2x squared minus 8x. Factor out an x. Are there factors of 8 that subtract to 2? Yeah, 4 and 2. Okay, so good. This actually factors. So that gives me x plus 4 minus 2. So my three answers in this case are for this one, 0. From this one, negative 4. And from this one, a positive 2. Okay. And for C, I should distribute these. Okay, so that's x to the third. Let's clear this out. Let's get some room for this one. X to the third plus 8x squared is equal to 8x plus 8. Move everything to the left side. And this should, if there's four terms here and it's a cubic expression, we really currently only have one technique in order to factor this. We're going to use a lot more, okay? But for now, the only way to factor this is by grouping. So group those two, has an x squared in common. That's x plus 8. Group these two, take out a minus, take out a minus 8, and that's x plus 1. So this one currently, unless I made a little mistake here, x to the third, 8x squared, yeah, minus 8x minus 8, okay. Our current repertoire of problem-solving techniques does not include a way to solve this, okay? So we'll have to come back to this after we learn some new tricks. Okay? But what you could have used in that case is a graphing calculator. Okay, so what are the real solutions to this equation? So I have graphed this already. I will say a few things first. If you just graph these two the way they are, okay, these are what your two graphs will look like. Okay, and it would be tempting to say, okay, I want to know where these two equations are equal to each other. So what does that mean? It says, where do they cross? So you would typically say, oh, right, just right there and right there, okay? But if you had zoomed way out, if you had made this graph really, really small, you'll see that there's another intercept point way up there, okay? And it's actually very hard to tell. So that is not the best way to graph this. The better way to graph this would have been to rewrite this equation by setting it equal to 0 and then plugging it into my graphing calculator, where you would get something that looks like this. Now this is very easy to tell the 3 places where this graph crosses the x-axis. They're not nice numbers. That doesn't matter, okay? That's why we use a graphing calculator, right? Unfortunately, the graphing calculator doesn't give me the irrational value, the radical value for those 3 points, but it gives me the answer close enough. Okay, so when you're using a graphing calculator, the only trick I'll tell you is set it equal to 0. It usually will make the problem easier to figure out. Okay, let's try a word problem that you could graph with a graphing calculator. Okay, so the first one, the hardest thing is to write the equation. So close friends Stacy, Una, and Amir are all born on July 4th. Stacy is 1 year younger than Una. Una is 2 years younger than Amir. On July 4, 2010, the product of their ages was 2,300 more than the sum of their ages. Okay, so let's say that X is Una's age. So that means that Stacy, whoops, that's how my wife spells Stacy with an E, is X minus 1. And Amir is X plus 2. Okay, right? Because Una's 2 years younger, that means his age is 2 years older. All right? So now the equation that we're going to have is that the sum of their ages is, the product of their ages is X times X minus 1 times X plus 2. So the product is 2,300 more than the sum. So if I want to make these two sides equal, I either need to take it away from there or add it to that side, which is what I'm going to do because I left more room on that side. Okay, so you could try to graph it this way. Again, not the best idea because it's easier to set it equal to 0. This is addition, so that's 3x. Minus 1 plus 2 plus 2,300 is 2,301. Then that's x squared minus x times x plus 2. And that's x to the third, first, outside, inside, and last. X squared, sorry, minus 2x. And setting everything equal to 0, moving everything over to, let's move everything this way in order to keep this positive. So we have x to the third. The two x squareds add together. The minus 2x minus 3x from both sides. Minus 5. And minus 2,301, setting that equal to 0. Now, again, not a pretty polynomial to try to factor. Best to graph it. And I couldn't fit the whole graph on here, but it goes way up and way back down. But basically, you see that we have now solved for x using a graphing calculator, and we get that this intercepts at 13. That means she is 13, she is 12, and he is 15. Okay. Before we finish, I want to do one more of these. Okay. So factor that polynomial. Remember that this is the difference of two perfect cubes. So the formula for the difference of two perfect cubes is same sign, opposite sign, always positive. Okay? So this factors, so x to the third minus 27. If I'm going to factor that, it would factor into x, right? Just what makes this, right? What are the three things that multiply together to give you 27? It's 3 and times 3 times 3. X squared, right? The first term squared. Multiply these two together and square it one more time there. And the signs go same sign, opposite sign, always positive. Okay? And then if I'm solving this, this one would equal 3. This one I need to use the quadratic formula always, and it's going to give me an imaginary number having something to do with the square root of 3. Okay? Looking at number 7 real quick, identify each expression as the sum of cubes, difference of squares. Perfect squares, difference of cubes, sum of cubes, difference of two perfect squares. Easy as that. Focus on the variable and decide whether you're going to use an old technique or a new technique. Okay. We haven't done a sum yet, so let's factor the sum. X to the third plus 8 will factor into x, same sign, opposite sign, always positive. Right? The formula is the same here. The pattern is the same. The difference is the signs. And that is 5-3, solving polynomial equations.